Hello, everyone. And but I would like to present, not just to show you my slides, right? Yes, this is it. Hello, everyone. And thank you so much, Nicola, for the invitation to New Zealand, to Multicore, and of course to discover not only the community, but the landscape in the country, which looks very similar to Switzerland. Nicola announced that I'm coming from Switzerland, and I was very impressed to discover the Alps, the Southern Alps. And of course, not only that. So I will be telling you today my experience and journey on the path of performance and portability, and whether these constitute pathways for the era of heterogeneous computing or not. That's up for discussion at the end of the talk. Yeah, but I was invited also to introduce myself in the local style, and because I have a multicultural experience of life, I would like to tell you that beyond my name, which is now written in Maori, I have arrived to Switzerland via Romania, where I was born, Greece, where I did my PhD, USA, where I did a postdoc, Germany, where I did a second postdoc, and now I work in Switzerland and I live in France. And in Switzerland, we have the river Rhine, which actually unifies three countries, Germany, France, and Switzerland. And I grew up near a very small mountain in the Carpathian Mountains in Romania called Meseș. And then I think that covers it. Because I mentioned the Rhine, right? This is the river. It is very close to the office at the University of Basel. The University of Basel, very few people know, and even I didn't know until I arrived there, is the oldest university of Switzerland. It was founded in 1460, and it has illustrious people such as Bernoulli, Euler, and many other Nobel Prize winners, also in medicine, philosophy, and other disciplines. So we are in one of the 7 faculties of the university, in the Faculty of Science, and we're one of the 7 departments of this faculty, uniting the very old tradition of mathematics, where Euler and Bernoulli were active, with the newest science of computers. And our group has been established 10 years ago, and it actually looks like that. We also like to have high performance fun, and this is maybe not an accurate picture, but, people come and go, but the fun remains. Our mission is to develop performance optimization solutions that advance the theory of parallel computing, broaden the practice of that theory, and of course expands where high performance computing, communication, and data analysis is used. And that involves sometimes algorithmic work, or applications, or working in the middleware, or trying out different systems. And as we do that, we have to face several questions. Of course, everything is about performance, but not only resilience, security, and sustainability, because we cannot ignore everything in the name of performance. And these questions become also our optimization goals. I think I shouldn't go too far. Right? And of course, we have to also solve some challenges along the way. But for that, we either use existing tools and techniques, or expand them, or develop new ones. And today I will be talking about performance and portability, with a focus on scheduling and programming models. Performance, like I will not have to convince you much, right? Because you're an expert audience, that performance has advanced in the many decades before, in the last half a century. And of course, it advanced because we have more transistors on a chip, because thread performance has increased, clock frequency has increased up to the point where all of them saturated, because of power limitations, which was overcome by the increasing number of cores. And of course, now the accelerators are missing from this plot, but performance is important, and that is why it is half the title of my talk. And we know all the milestones that we have seen, that also all of these advances were incarnated in vector computers, in clusters that contain those vector units, in increasingly heterogeneous hardware and increasingly scalable systems, with different other milestones from the applications and from the programming models. Right? But any architectural innovation in hardware is disruptive for the software. And some labs were rich enough or fortunate enough to acquire enough funding to port their legacy and important codes to machines such as the Lassen machine that had GPUs, but not everybody can do that, right? So Because hardware has evolved and performance has evolved, this also is reflected in the adoption and advances in programming languages and programming models actually for parallel computing. And we see what we typically use these days, right? And the most recent addition is Intel One API. But any optimization for a specific hardware has a short lifespan. So this brings us to the question of, okay, we have performance, we can, in hardware, we have programming models that can exploit that performance, but what about portability between those systems and programming languages? So let's explore a little bit of that balance, right? And we put it all together. Excuse me, I think I'm pressing the wrong buttons here. We put it all together that we have more and more diverse applications, because as more performance we have in the systems these days, more users become aware of such advances in performance and programming models that need them. And that leads to the fact that not all applications run on all architectures, which is true and will only continue to remain true in the future. And we have different ways of exploring the balance between performance and portability using languages and libraries, directives and APIs, frameworks, higher level programming frameworks, and of course, domain-specific languages. And I highlighted in yellow the ones that we will be focusing on today. But how are we going to compose elements from here, from these frameworks, libraries, and languages to achieve scalability, performance, and portability? We have MPI plus what, or do we have something entirely new? So let's look at the case where X, MPI plus X, is MPI plus OpenMP, because this is widely used in scientific applications and benchmarks. We looked with one of my PhD students in over 100 codes at the beginning, because he wanted to do scheduling in OpenMP, right? And I said, okay, let's make sure that there is a need for that, right? So he looked at well-known applications, benchmarks, and checked for what are the most commonly encountered features. And we see, I'm sorry that this is too small to see, but what we should be looking at is the first column, because this represents the for loops. And we see that the numbers, first of all, exist for every application. So every application uses at least one for loop. But if the number has more than one digit, that means that there are so many loop instances in those applications, which tells us that this was a worthy problem to study. And then the question was, which scheduling is most needed and most efficient for each of these applications, assuming they run only on one system, but they could be running, of course, on any available system, right? And the OpenMP standard offers a few choices, which are great to start with, but maybe not sufficient for the needs of parallel applications and architectures. And the chunk parameter doesn't have the same meaning for those, even for those 3 available or 4 available techniques, because the auto falls back to one of those 3 depending on the implementation. So we know that one size, even if the portfolio here is very small, doesn't fit all. And the question we still need to answer is, we have more than one loop in an application, as we have seen before, right? Do we use the same schedule for each of those loops? Or do they have all the same characteristics? Obviously not. But those many loops may be encapsulated in time steps, right? For iterative applications, which are classical HPC codes, but also new AI codes, right? This is actually daily business. And then every application has a different set of time steps and a different set of loops. And when you put the system, then all of this becomes a not easy choice. Definitely one size doesn't fit all. So you have to have a specific solution for each of these instances of these loops. So, sorry. So, but it's important to remember that it's not a free lunch theorem, right? So even if you have an answer for this loop in this time step on this application in this time system, I'm using scheduling method X. As soon as you change anything here, you might have to choose a different scheduling method. So it's important to remember that if a method works in some cases, others will work better in the remaining cases and vice versa. So for that, we introduced a scheduling library. And because that scheduling library now has tens of scheduling algorithms, we also introduced an algorithm selection method or approach for auto-tuning to dynamically select the right algorithm at runtime for the case of tuple that is needed. And I keep going far away. So for that, we have developed scheduling libraries. Let's focus today on the load balancing for OpenMP scheduling library. Initially, it was implemented in the GNU implementation of the OpenMP runtime, and now it is implemented in the LLVM OpenMP runtime. And we have here 20. I try to do this. It doesn't work. I have to go closer. We have 20 scheduling algorithms in the LB4 OpenMP library, from which we selected a few to put in 2 portfolios. Here we have 12 of those 20 scheduling algorithms and 3 ways to select from those 12 using expert rules, because we have expertise in scheduling and we wanted to codify them in rules and not only follow the hype of machine learning, but also not ignore our expertise. But we also wanted to look at reinforcement learning approaches, and for that we have the other portfolio, which has the same scheduling algorithms, but 2 different selection methods and 2 different rewards. And with this, we want to close the gap between what's available in the literature and what's available in practice, and use, of course, also AI to help us select the right algorithms at runtime. And also, this gives us a fair way of comparing and evaluating algorithms, which is direly missing in the literature. Yes, let me walk you through this. This can be a little bit imposing. So what we did, we tried to test our scheduling library for applications that have MPI and OpenMP, and we only changed the OpenMP part. We changed the loops. We dynamically selected a right scheduling technique for the loop. But let me tell you what these are. This is a pure compute-bound application. It has very little memory accesses, so we wanted to see what works for that. Here we have a pure memory-bound application, the stream triad benchmark. And here we have 3 applications that, depending on their phases, can be compute or memory-bound. And each of these applications was run on 3 different systems, on maybe a little bit older Broadway architecture, Cascade Lake, and a recent Epic AMD machine. And here we have the case where Oracle is, if you knew from a magic crystal ball the right technique to choose at every instance, you would be Oracle, and this would be the execution time that you would achieve and you achieve on these particular machines for these applications. But if you use an expert-based selection algorithm with certain parameters, or a reinforcement learning-based method with other parameters, you are so far away from the Oracle. The lighter colors means closer, so 8.2% within the Oracle, and here you have over 400% away from the Oracle. So basically you missed the mark. So let's have a closer look at why certain techniques perform even better than the Oracle or worse than the Oracle. And remember that this is an application that has time stepping. We evaluated it for 1 loop over 500 time steps. So this is just the outcome of 500 selections. So then the answer will be in how the selection happened at every time step. We have here the Oracle selection, and these are the 1 loop, which is the gravity loop in an OpenMP node for this application, iterated over 500 times. And we see lower is better, so the execution time of each of those loops was optimally executed with dynamic, and 30 as the chunk parameter, and other techniques it performed different selections. What characterizes expert selection is that they have a short exploration phase, whereas reinforcement learning techniques have a longer exploration phase because they are model free. They are not pre-trained. They are learning as the loop starts executing what is actually useful from the portfolio of scheduling algorithms. So they're trying with particular learning policies and rewards what is the best technique. And then they exploit. This is called the exploitation phase. And some of those exploitation leads to suboptimal selections or to an indecision. And one of the techniques in each category leads to close to optimal selection after the exploration phase has happened. So what we see is that for applications that have time to learn, the exploration phase might be longer with reinforcement learning technique, or might be shorter if you use an expert method. And this just goes to show that for this particular instance, you might want to benefit from expert-based methods instead of reinforcement learning, just because it is the hype. But now let's look at a case where X or Y, in this case, actually we have a different name, is not OpenMP, but it is CUDA or HIP or SICKLE. And we study this in the context of an application that performs hydrodynamics using the smoothed particle hydrodynamics method and also gravity to study the different phenomena such as the formation of stars or galaxies in cosmology. This application has 4 components: a front end, domain decomposition, state-of-the-art SPH methods, solvers, and a gravity solver. And Rio, the developer of this gravity solver, is in the room, so you can ask him questions about why this solver is cool and scalable. So this is an application that is actually the flagship code for the SKA consortium in Switzerland, with which we want to execute simulations, mock simulations that will be compared to the observations of the SKA once we start having data coming in. But let's look at the number of lines of code in each of these modules, and we can see that we are not doing bad. We have enough number of lines of code, out of which a significant number is ported to the GPU using these 3 programming models: CUDA, HIP, or SICKLE. And what was our approach for portability and performance exploration? We first started with C++ code that was directly coded for CUDA, right? Because we had the CSCS PISDINE supercomputer out there, and we wanted to start our simulations on PISDINE. And we saw that performance increased, and I will show you some results. We achieved incredible performance numbers at high efficiency, but we were not portable. And because Switzerland is also a contributor and part of the consortium that operates LUMI, we wanted to port our code to LUMI because there was a time until PISDINE was decommissioned and ALPS was introduced, which was in the fall of 24. So we used Hipify in place. We have the same number of lines of code. We had no errors in the portability, in the porting. The performance decreased a little bit because the system was not perfectly stable at the beginning, especially in the communication libraries between the GPUs and on the GPU, but portability increased, right? So we had to pay a little bit of performance, but we have to gain in portability. And now we are exploring with a master student Intel One API, so porting to SICKLE, and we will see, I have a slide, but I don't have results to show that the number of lines of code increases significantly. Performance is expected to decrease, but we haven't been able to run the code. But portability absolutely, definitely increases, because then you can run on AMD GPUs, on Intel GPUs, but also on AMD and NVIDIA GPUs with just one code, right? So of course, we also have some dependencies, and of course this is only the simulation part, but it is integrated with data analysis pipelines for visualization or snapshot analysis. I promised you that I will show you the number of lines of code. So this is maybe not a one-to-one mapping to the modules that I've shown you at the beginning, but here we have the domain decomposition, some external libraries such as ADF5 or a Grackle module. Here we have the main front end, some other physics, the gravity solver, and the SPH part, the hydrodynamics part. And here we see that the number of lines of code in the pure C code, not the header, the code is increased from the CUDA or HIP version, so C++, C or C++, we should compare the headers and we should compare the codes this way and the codes this way, right? So darker means a higher number of lines of code, and this is because some modules couldn't be ported with Cyclomatic, with DPCT tool immediately, and had to be ported file by file, but we're still exploring because we have a high number of errors, right? So portability here is not equivalent to high productivity. But except for this particular portability issue, we are interested and we are delivering SPHexa, which is a highly productive code, as a simple mini app, easy to run once we have the code ported to HIP on CUDA, which we do. So let me show you some scalability results that we achieved with CUDA. We achieved them first on PISDINE, the older supercomputer at CSCS, and due to algorithmic improvement. So we had the CUDA version, But then we had some algorithmic improvement developments. They achieved an impressive factor of 13x performance. And for that, we started initially with a naive implementation of the domain decomposition that was moved to the GPU. Then we eliminated all the host device transfers. Then we made the search for neighbors GPU aware, so we optimize for the particular architecture. And then we now explore also mixed precision because we want to have multiple particles of different gases and they don't need the same amount of fields. And this also allows us to store more particles on the GPU such that we can do more simulations on the available machine. But when we go to Lumi, which we did after we had that improvement scalability on PISDINT, we have scaled to a very large number. So a trillion particle, trillion particle simulation only on a third of Lumi, the G partition. But for one of those data points, actually, because we started, we improved algorithmically how many particles need to perform a certain time step calculation. So instead, because there are regions in the simulation where some particles need to have a more refined time step. This is not a mesh code. This is a particle code. So it's comparable to what you see in adaptive mesh refinement. Here it's an adaptive time refinement for certain particles. And that allowed us to gain a 4x performance improvement. So basically do more work in less amount of time. But going back to HEAP, we are, I wanted to say, so based on that result, there's another plot. Based on that result, we were able to achieve the largest ever allocation on Lumi, actually, 25% of Lumi for 1 year, to study the role of turbulence, which is the turbulence, it's an emerging phenomenon, and the role of turbulence and gravity in the formation of stars. So for that, we have a simulation plan that takes us from small simulations to very large simulation in a cubic domain, requiring weak scaling, data compression, visualization, workflows, right? We heard yesterday a lot about workflows and how important they are these days. And of course, we have some intermediate optimizations, such as particle splitting. So to generate the initial conditions for some important intermediate scale resolution simulations, we do some tricks such as particle splitting, and the physicists can explain this better. What this shows here is a simulation plan and also some concurrency between the simulations, because these will create the initial conditions for this, but some of these are independent, so it means we can fully utilize the machine. It doesn't mean we did, but that was the simulation plan. So let me tell you some performance numbers that we achieved for the low resolution run with only 128 nodes, by having every particle do only a global step, which was adapted at every time instance. We needed 250,000 GPU hours, but by implementing individual time steps, only some particles go to final resolution times. This was improved by a factor of more than 3%, three times. For the medium resolution 5,000 cube, we on much more nodes, on the 512 nodes, we needed over 100,000 GPU hours, and the checkpoints that require, this simulation took 9 days. We have a checkpoint after every 24 hours, and that totals up to 82 terabytes. And the largest simulation that we're currently still running, actually our allocation ends tomorrow, so it's been a year and 3 months, and I'm not sure if we can finish it because we would need 14 days. And for every day, we will need to save a snapshot of 73 terabytes, which for the entire simulation would be in the order of petabytes. This only goes to show that we actually need data reduction, data compression, and in-flight without saving them to analyze the data. So I wanted to, this is the slide that I wanted to mention, that we also ported with no change, no algorithmic change, no programming model change to the ALPS supercomputer at CSCS, and we achieved quite high % efficiency on 2/3 of ALPS. So this shows us that we are both portable and performant once we have the code that works on the machine. So programming for portability, I'm trying to put my code there according to the quotes I've had before on the slides. Programming for portability fuels adaptivity and then unlocks performance, which we have. But does this work for everybody else, including workflows, which we also so desperately need? I don't know, but let's see. We have the final result that I wanted to discuss with you today, the Z part, which I have not explained so far. Well, we see increasingly more and more simulation code, such as Pick on GPU, that was presented yesterday by Sunita. I'll wrap up fast. Data management and machine learning, right? So what if we would be able to integrate them? Because if you see, they use a lot of frameworks, and that's harder to integrate, right? So this is where a project that recently completed the European Union project, Daphne, comes to the rescue. And I will not be able to go through all the details, or else I will be tragically over time. So let me go to the bottom line. Oh, try to find my mouse. Ah, I found it. The bottom line is, and this is where I can tell you more about Z. It's a domain-specific language that comes with a runtime that performs task scheduling, in which we implemented the scheduling methods that I have shown you also in the first part of the work. Here we didn't have any scheduling because it was a very GPU-centric code, right? So there, the bottom line here was that we have portability with a small decrease in performance, but we have no dependencies and no effort to scale to the parallelism in a single node or to the parallelism across nodes. So putting it all together, the methodology I've just explained, there are efforts. This was a single PI effort and a single PhD student, several years, many people, a few years, even more people to develop this result. So it's not without limitations, and there is future work that we want to perform for each of these. The goal is, please spread the word about these libraries, codes, and tools because they are open, and we want to increase our user base. And now I'm getting to the very last slide where I give you my answer on performance and portability, and maybe we can have a discussion. If we invest in DSAs, domain-specific languages, and domain-specific architectures, we favor performance and sacrifice portabilities. But that's maybe what we need to do for some applications. But if we want to favor portability, we might want to invest in transpilers. And here there was some work chat. HPC could come into play where we easily port modules and pieces of the code to any architecture that we can and we need to. But the path towards performance and portability actually involves a balance between the two in where we can see these early stage and high expectation technologies, exascale computing, AI, energy efficiency, distributed, actually can become a mainstream technology. It isn't yet, but they can become mainstream technologies that are widely adopted. But those technologies where programming models reside are actually widely adopted, and they are the key to make these technologies that are now early stage and everybody's excited about exascale and AI outside of our community. They can, if we innovate in programming models that are both performant and portable, then we can achieve these innovations. And I'm asking everyone to support and fund such research and prioritize impact whenever you review a paper or proposal and not novelty or hype. Thank you very much.